Hello and welcome to part 2 of chapter 14. We're going to be looking at the ethers, aldehydes, and ketones today. So let's start off looking at our ethers. So an ether is a compound with an oxygen bonded to two organic groups. So basically it's an oxygen bonded to two carbons in the main chain. So we look at our electron density, we see that we have an oxygen in the middle of our chain. But we could also see that it's kind of surrounded by all of this nonpolar electron density. So we're going to find that it's mostly going to act like a nonpolar group. So the general form of an ether is an ROR. So remember, R is just any kind of a carbon group. So it can be aliphatic or aromatic. So I could have our aromatic rings as one of our groups. These are slightly polar, like we said, because it does have a CO bond in there, but it doesn't have hydrogen bonding to one another since there's no hydrogen attached to this oxygen. So if we look at the physical properties of ether and compare them to both just a hydrocarbon chain and something like our alcohol group, which does have hydrogen bonding, the boiling point's much more similar to our hydrocarbon chain. So although it does increase it slightly, because there is a little bit more intermolecular forces because that oxygen is or does have a slight negative charge. However, when you're comparing it to something like an alcohol group with similar molecular weights, not even close. So we see that the boiling point is much higher, so it's got much stronger intermolecular forces with the alcohol than an ether or the hydrocarbon group. So some more properties of ethers. Once again, because of that oxygen, although it can't form hydrogen bonds with itself, it can form hydrogen bonds with water, since water has the OH, and that H can interact with this oxygen. So it does make it so that some ethers, or low molecular weight ethers, are soluble in water, but once those organic groups get large enough on either side, they kind of envelop that oxygen, so they can't interact any longer with the water. Now another very distinct property of ethers is that they are highly flammable. And this is actually the compound that when you hear of meth labs exploding, it's the ether that they're using to create their meth that actually explodes, that actually ignites with any kind of burner. So they are highly, highly flammable compounds. Now we're actually going to name ethers using their common name. Although I'll show you their IUPAC name as well, everybody uses their common names. So you very actually rarely see the IUPAC name. So the way that we're going to name it is we're going to identify the two organic groups and then add the word ether. So in this case, I've got two methyl groups on either side, so it'll be a dimethyl ether. For this molecule here, I have an ethyl-methyl ether, so I have an ethyl group and a methyl group, so ethyl-methyl ether, so we're doing it alphabetical. And here I've got two ethyl groups on either side, so it's a diethyl ether. Now, just like inorganic compounds, there are just common names for compounds that are commonly used, but don't necessarily follow all of the IUPAC naming. So one of them is our ethylene oxide. Notice the big ring strain in this compound, this triangle. We know that carbon wants to form 109 degrees apart, but when I have a ring of only three elements, it makes it very, very strained. So this makes it a very reactive compound. So this is a very easy way to add an epoxy, so it can be used as epoxies. It kind of glues things together if it reacts with other molecules. It also is used as a disinfectant. So ethylene oxide is actually used for a lot in hospitals for equipment that can't be sterilized using steam. So if something melts when it gets too hot, they'll typically coat it in ethylene oxide instead, and that'll disinfect it. The catch is that it does leave a residue, so you have to make sure that the residue is gone before you actually use the equipment. So it's actually tested and monitored that you sterilize something in ethylene oxide, you go and test it, make sure that your setup doesn't leave very much residue, so that way it doesn't hurt the patient or hurt whoever is going to use it later on. So this is, like I said, fairly common, and it's actually even shortened even further for the name, and most of the time you hear it just as EO. It's been sterilized through EO. So EO is our ethylene oxide. Our other two are the hydrofuron and 1,4-dioxane. These are really good common organic solvents that used to dissolve things and have other things react in the actual solvent, or in these two solvents. Alright, so let's do a couple practice problems with naming these ethers. So go ahead and pause it and see if we can name these two ethers. Alright, so if we look at the two groups attached on either side of this oxygen, I have a methyl group here, and I have a 3-carbon chain, 1, 2, 3, but it's attached at the second carbon. So that makes it an isopropyl group. So it's propyl because there's 3, iso because it's attached at that second one. I comes before M, so this makes it an isopropyl methyl ether. Now for our second one, I have an ethyl group here. And we see that it's a benzene ring, but it's a substituent off that oxygen, so we're going to call it a phenyl group. So that makes this an E comes before P, so it's an ethyl phenyl ether. So that is the way I'm going to want you to name these ethers. I will show you the IUPAC nomenclature, so in case that you do happen upon it, you have seen it, but I'm going to want you to name it using this common method. Alright, so let's look at the IUPAC rules. So the IUPAC names is based off of the longest chain attached to the oxygen. So whatever the longest chain is, that's what we're going to name it off of. The shorter chain then is named as an alkoxy substitute. So we're going to take that alkane, replace it with oxy. So in this case, I've got 2 carbons, so it's an ethoxy. Alright, so let's look at an example. So I've got a methyl group here and a 1, 2, 3, 4, 5 carbon chain here. So we said we're going to name it off of the longest chain. So this is a pentane molecule. And then we're going to name the shorter chain as a methoxy group. So we've got a 1-methoxy pentane. So if you see anything with a carbon chain and an oxy, so ethoxy, propoxy, whatever, that is the IUPAC naming for our ethers. Now, although we said that these ethers are highly flammable or they're easily oxidized in air, otherwise they're fairly chemically inert, since they just have some long carbon chains attached to them. So they do not normally react with acids and bases, but like we said, they are extremely volatile. Now to actually create an ether, we actually can dehydrate 2 alcohol molecules. So recall that a dehydration reaction means that we're taking away water. So if I look at this reaction here, I have 2 ethanol groups, and if I add some acid and heat it up, what's going to happen is that a water, so notice it's H2O, so it's 2 H's and an O, get removed, and the rest combines into an ether. So I get water as a byproduct, so 1 alcohol and 1 hydrogen get removed to form water, and the rest makes an ether. So that's the main reaction of how to prepare an ether. So let's look at a few more uses of why do we need these ethers? Well, ethers were actually used commonly as anesthetics for a long time. So they accumulate in the lipid material of nerve cells interfering with nerve impulses. So you don't feel what the surgery or whatever you need to make you healthy. So the catch, we know that they're very flammable, so you don't really want to be working with these ethers. So what they're doing today is they're halogenating them, so that's used as general anesthetics. So if we look at this guy here, the halogenated ones, I took the two hydrogens off and added some fluorines and chlorines. This makes it a whole heck of a lot less flammable and safer to store and safer to work with. But that was the most common use of diethyl ether for a long time. It was the first successful general anesthetic. So a pretty cool compound to use, except that it's flammable. So they just modified it slightly to make it less flammable, and it still works very well. Alright, so another compound that are very similar to these ethers are sulfides. So we're going to call it a sulfur analog of the ether. So instead of having an O here for an ether, I'm going to replace it with a sulfur instead. So once again, we're going to use the common names for these. So we're going to name these the exact same way as we named our ethers. So instead of having a dimethyl ether, we're going to put it as a dimethyl sulfide, or a ethyl methyl sulfide, or a dimethyl sulfide. So we're naming these, like you said, the exact same way, or just changing the word from ether to sulfide, since I've got a sulfur compound in there. So we'll notice that just like our ethers and our sulfides, we can replace a sulfur with an oxygen in most of our compounds, because they're going to react very similarly. So in this case, instead of replacing it in an ether, we can replace it also in an alcohol group, and we're going to call these thiols. So the systematic name for a thiol formation is just adding the word thiol to the parent hydrocarbon name. So we're just going to name whatever hydrocarbon it is. So in this case, I have an ethane, and I've got an SH at the end, so I'm going to put the word thiol. Here I've got a 1, 2, 3, 4, so it's a butane. Notice I got to keep the SH at the 1, so I have to say where that SH is. And then I'm numbering it from there, so this is a 3-methyl. So 3-methyl 1-butane thiol. Now what's special about these thiols is that they have a characteristically foul smell. This is when you think of a sulfur smelling bad, it's these thiol groups that the sulfur just smells terrible. So what do I mean by smelling terrible? It's in the defensive spray of the North American striped skunk. So that terrible skunk smell that you get when a skunk gets scared is a thiol group. It's also kind of the not pleasant smell of the onions and garlic that has thiols. So anything that has a thiol group is not going to smell very pleasant. Alright, so let's look at a couple more examples of naming these thiol groups. So we looked at this one earlier. We're just naming the parent chain. So in this case, we had the butane, and we're naming it off of that sulfur compound. So 1, 2, 3 methyl, and then our butane thiol. Alright, so here's a couple new ones. I've got an ethane group here, but now I have two thiol groups. So it is a 1,2-ethane diol. So notice I have the di meaning 2. So whenever we have 2 of something, we're going to put that word di. So we have to say where they are, and then we say how many. In this case, I've moved the sulfur group over. So now it's a 1, 2, 3, 4. So 1,4-pentane dithiol. Alright, let's give one for you to try. So let's name this following thiol. So go ahead and take a couple minutes and name this one. Alright, so we named the longest chain 1, 2, 3, 4. we start the numbering at the thiol group, so it's 1, 2, 3 methyl, 1 butane thiol. Now these sulfur groups are fairly, you can use them a lot of different ways. So if I take 2 of these thiols and react them with a mild oxidizing agent, we're going to yield a disulfide compound. So it's an RSSR. So now I have 2 of them in our chain. So the way these SS bonds typically work is that I've got 2 thiol groups, I have some kind of mild oxidizing agent, and they combine, drop their H's, and I form a covalent bond. Notice when I did that, I get this 3-dimensional shape. So it goes from a flat chain to giving it a few little bit of 3-dimensional shape. So this is what that helps give those protein molecules their required shapes to function in our bodies. So when we look at the different shapes of the proteins and the different degrees of them, we'll see that these thiol groups are what kind of give those groups their shape. So it doesn't just happen inside our bodies with their proteins, but it also happens with hair proteins. So when somebody gets a perm, what they're doing is they're creating disulfide, or they're taking those disulfide bonds and they're broken and new ones are formed to give hair a different shape. So you want a perm, well, they're going to break those bonds and those little curls in the proteins are going to occur, and on a macro scale it actually curls your hair. So for those of us that all have curly hair, it just means that we have a whole lot of disulfide bonds in our hair. For those of you that have just bone straight hair, well, it means you just don't have any disulfide bonds. But if you wanted curly hair, you can go put some oxidizing agent in, heat it up, and you get your disulfide bonds and the curls. It also works with chemically straightening. So for those of you that didn't want curly hair, you can chemically straighten it. What does it mean to chemically straighten? It means that you're going to reduce those bonds. So if oxidizing forms them, reducing breaks them apart. So you can actually break those bonds apart and straighten your hair as well. So there's actually a lot of chemistry going on in the salon. So here is that reaction in chemistry form. So our molecules. So we have this thiol disulfide redox pair, and it's a critical factor in protein structures and our bridges. So I've got 2 cysteine molecules here. I see that if I'm oxidizing it, I'm getting rid of those 2 oxygens, or sorry, 2 hydrogens. They're popping off, and I'm forming that disulfide bond. But if I want to get rid of that disulfide bond, I'm going to reduce it, add those hydrogens back in. Here is one more example of where you see these disulfide bonds. You see it in the molecule insulin. So this helps regulate our blood sugar. We're going to talk a lot about insulin when we get to, I think it's like chapter 19-20, so later on in this class, when we talk about diabetes and how all of this is regulated. But we see that in our chains of insulin, we have these disulfide bonds throughout the chains, holding them together. So last thing with the physical properties of these thiols, sulfides, and disulfides, they don't have any hydrogen bonds. So remember, hydrogen bonds is nitrogen, oxygen, fluorine with a hydrogen. So since they don't form hydrogen bonds, they do have dipole-dipoles, but they don't have as high as boiling points as something with a hydrogen bond. So it'll still be higher than just a normal hydrocarbon chain, but it's going to be lower than our alcohols. So I have one of these bubbling pools. You see these a lot in Yellowstone or anything that has a lot of volcanic activity around. These mud pools emit a very nasty smell, so it's that nauseating smell. Well, we just found out that that nauseating smell that comes from these mud pools are the thiols, sulfides, and disulfides, mostly the thiols. So that kind of putrid smell that you get when you walk around all of the geyser pools and such is a thiol that's coming out of the earth. You could also see it as this yellow around the pool. The yellow is actually just pure sulfur that's hanging out, or that got precipitated out of the pool. Alright, so let's shift gears and talk about our aldehydes and ketones. So what makes aldehydes and ketones special is that they have this carboxylic carbon. So a carboxylic or carbonyl carbon is a C double bond O. That is going to be very characteristic of these aldehyde and ketone groups. So these are strongly polarized with a partial positive and partial negative charges. So this partial positive, partial negative. So that anytime we have a partial positive, partial negative charge, that is going to make it a very reactive site. So there's going to be a lot of chemistry going on in this carbonyl carbon compound. So here are all of the functional groups with this carbonyl carbon. We're just going to talk about aldehydes and ketones in this chapter, and in our next chapter we'll talk about carboxylic acids, ethers, and amides. But notice that they all have this carbonyl compound, and then what's attached to it is what is different. So an aldehyde has a hydrogen attached, so it means it's always at the end of a chain. A ketone has two carbons attached, so it means it's always in the middle of a carbon chain. Carboxylic acid has an OH, so once again it has to be at the end of a chain. Ester has two O's and two R's, so it has to be in the middle of a chain. And then our amides has a carbon and a nitrogen attached to it. So here are the generic structures of an aldehyde and a ketone. We said aldehydes have some R group, some carbon chain attached with a hydrogen at the end. So that is specifically what makes it an aldehyde, is this hydrogen. The ketone then has two carbon groups. They can be the same carbon group or they can be different, which is why this one has a little apostrophe here. Just means that they could be two different groups. So I want you to draw these in your notes so that way you have reference of what exactly they're going to look like. Now we're going to get into naming aldehydes and ketones, and I am going to want you to use the IUPAC names for these ones, but you are familiar with some of the common names for these. So one of them was formaldehyde. You know that formaldehyde was way back when used to preserve specimens, like in the jars, but more commonly today it's used in building materials. So you think of particle board, so that kind of mash of all of the wood that's put together. That is helped or held together using or the chemical reaction using formaldehyde. Now, most people are pretty sensitive to formaldehyde. So when you have these building materials, theoretically you'll want them to have all of been degassed of these formaldehyde. But if it's not made correctly, there's still a lot of formaldehyde in it and the gas keeps coming out. So this is what happened in Louisiana during Hurricane Katrina. The rebuilding of Hurricane Katrina, they brought in all of these portable houses. So portables that they kind of made into houses. So they were manufactured very quickly and very cheaply. The catch is that they were using a lot of particle board that was not made correctly and had a lot of formaldehyde still in it. So they had all of these wonderful makeshift houses for people to live in while their houses were being rebuilt, but nobody could actually live in them because everybody was getting sick because of all of the formaldehyde that was in them. So they actually ended up just sitting empty and not being used because of this. So if you ever get particle board and you kind of start getting headaches when you're around that desk or that dresser or whatever the particle board is made out of, it might be the formaldehyde in them. The second one here is acetaldehyde. Now you may not have heard of this in person, like you may not be familiar with the name, but it is one of the most common aldehydes in nature. You can find it in coffee, bread, ripe fruit, and it's actually with the byproduct in your alcohol dehydrogenase. which is how your body actually consumes alcohol, or how it gets rid of the alcohol that we drink. So since it's the byproduct of that, this is actually the molecule that causes hangovers. So your body doesn't like having this molecule in there, so it doesn't make you feel very good when it is formed. But it is less toxic than actually the alcohol in your body, which is why it's your body breaks the alcohol down into this acetaldehyde group. The last one here is benzaldehyde. Once again, you may not be familiar with the name, but you are familiar with the smell. This is kind of the fragrance of almonds. So in some foods and in perfumes, they'll flavor it with benzaldehyde. So it's kind of that synthetic almond taste that you can get. Now here are some of the examples of our ketones. Just like our aldehydes, some of them are known more commonly as their common names, but we want to focus on their IUPAC names here in a moment. But we are familiar with acetone. So this is a nail polish remover. So, or it removes paint really well. So it's basically a solvent. You can dissolve your nail polish with acetone. That's essentially what it's doing. Is it's a solvent. It's dissolving it. That's why it also works in kind of removing a lot of different stains as well. So if you have kind of a paint stain, you can use acetone to remove it. Ethyl methyl ketone, this is used a lot in, or it's another solvent. So this has a kind of a butterscotch type smell, and what it does is they'll use it as a solvent for printer ink. So, and other types of inks and adhesives. So they put all of the colorant into the ethyl methyl ketone, and that is what's spread out on your paper when you print. Then the ethyl methyl ketone is dries off, and you're just left with the ink color. So it's the solvent for like printer ink and adhesives and such like that. All right, so let's actually look at these IUPAC rules for aldehydes and ketones. So just like every other IUPAC rule, we always want to name the longest chain. But we want to name the longest chain with that carbonyl carbon in it. And with that carbonyl carbon having the lowest number possible. So in this case, it's 1, 2, 3, 4. So since that carbonyl carbon atom of an aldehyde is always in position 1, we don't need to specify it. It always has to be at the end of a chain for an aldehyde. So we don't need to ever say it's a 1 aldehyde because they're always going to be 1. However, with a ketone, we said by definition it has to be in the middle of a chain, so we are going to need to name or number where that ketone is. So unless the molecule is small enough that there is no question about where it can be, like propanone, it can't be at the end because then it would be an aldehyde. So the only carbon that can have the carbonyl is the middle one. So you don't need to say 2-propanone because it can't be anything else. However, for most compounds, they're going to be big enough, so have more carbons in the middle of the chain, that we will need to specify the number out front. Now, how to name that parent chain? We're going to drop the E, and for aldehydes, we're going to add the word or the suffix al to it. And for ketones, we're going to add the suffix "one." So it's propanone or 2-pentanone. And then we said for our aldehydes, we're going to add the suffix al. So methanal is formaldehyde because there's 1 carbon and it's an aldehyde group. For 2-carbon chain, ethanal. So we drop the E, add the al. So we have a 1, 2, 3, so it's a propanal with a 1,2-methyl, so a 2-methyl propanal. So propanone for our ketones, so 1, 2, 3 carbons, so propane, drop the E, add the ONE. We didn't put a 2 out front because we said that it can't be any other place. Here, for our next one, so we have 1, 2, 3, 4, 5, so it's a pentanone, and that ketone is on the second carbon. For this last one, I have 1, 2, 3, 4, 5, 6, 7 carbons. On the second one, I have a methyl group, and the third carbon has that carbonyl. So 2-methyl, 3-heptanone. Now I do have the common names under there for reference, but you do not need to know the common names. So just for summary, you need to know the common names for your ethers and your sulfides. But for everything else, we are going to be doing the IUPAC names. So we're looking for that longest chain, numbering where that functional group is, and then naming everything else that is attached to it. All right, so let's do a few practice problems. So for number 1, give the name of both of these compounds. And then for number 2, draw the structure for 4-methyl hexanal. Take a couple minutes and write these out. All right, so let's name these two compounds. So I have a 1, 2, 3, 4, 5, 6 carbon chain. And on the third carbon is where my carbonyl group is. So it'll be 3-hexanone. Now I've got an aldehyde group at the end here. So it's a 1, 2, 3 carbon group. So that makes it a propanal. Lastly, draw the structure for 4-methyl hexanal. So I'll have 6 carbons in my chain with an aldehyde group at the end. And on the 4th carbon, I'll also have a methyl group. So it should look like this. So here's my aldehyde group, and then on the 1, 2, 3, 4th carbon, I have my methyl group. All right, let's draw 2 more. So draw the line bond structures and give the systematic names for the following compounds. So you could either give the line bond or the skeletal structures. I'm okay with either one as long as you know what they look like. So go ahead and draw them and then name them. So the black ones are going to be carbons, the white ones, the white balls are hydrogens, the red ball is an oxygen. Alright, so for the first one I see I have an aldehyde group, a C double bond O with an H, and it's 1, 2, 3, 4, 5 carbons, so it'll be a pentanal with 1 carbon hanging off. So here would be the line bond structure or the structural formula. Like I said, you could draw this as a skeletal formula if you want. That would look like this. So that would be the skeletal structure. Now, technically, a lot of times you see an H here too. That H isn't necessary since it's a skeletal structure. So you could either write the H or not write the H. You see it both ways all the time. So I will accept either way. So you could either have the H or not have the H for the aldehydes. Alright, so then for our next compound, I have 1, 2, 3, 4, 5, 6 carbons in the chain. On the third carbon is the carbonyl, so we see that it's a ketone. And I've got a methyl group hanging on the 5th carbon. So 5-methyl, 3-hexanone. So let's draw the skeletal structure for this one as well. So here would be the skeletal structure. So 1, 2, 3, 4, 5, 6. And I have the ketone in the middle. Alright, so now that we know how to name our aldehydes and ketones, let's talk about some of their physical properties. So that carbonyl group makes the aldehydes and ketones moderately polar compounds. So although they don't form hydrogen bonds with each other, they can form hydrogen bonds with water using those electron pairs from water. So water has those slight positive and negatives, water has the OH, so it can form hydrogen bonds to the H in the water. So that does make these fairly water soluble. Once again, until you get too big, 5, 6, 7 carbons. So because they can't form hydrogen bonds with itself, just like our ethers, they do have lower boiling points than something like an alcohol. But notice it is higher than our ethers. So our butane, this is just our straight hydrocarbon, completely non-polar, boiling point of 0. So similar molecular weights, propanol 50, acetone 56, but we see the alcohols still are the top with our hydrogen bonding at 97. So they're still much higher than a hydrocarbon of or similar weight, but they are still much lower than our alcohol groups. So there are a couple things I wanted to point out in this table. The first one is the obvious one where the boiling point is going to increase with the increase in size. So you have the similar functional group, so if we add more carbons, we're adding more London dispersion forces, so we are adding more molecular forces, increasing the boiling point. Also notice that as we increase the number of carbons, we are decreasing that water solubility. So it's less and less soluble as we increase the number of carbons, because water wants something to be polar. The second thing I wanted to point out was the condensed structures of these aldehydes and ketones. So notice that to write a ketone or an aldehyde in condensed structure, they write it as a CHO. We know our alcohol groups were a COH. They write the aldehyde as a CHO. That is why it's very important to get the order correct for these functional groups. So anytime we see a CHO, it is an aldehyde group. Now, for these acetones or these ketones, there are a couple different ways of writing these as our condensed structures. So this is one, but I don't really like this way because it kind of makes it look like a ketone. A ether. But we know it's a ketone because this carbon here, the carbonyl carbon, doesn't have any hydrogens attached to it. So if it was a ether, there would be hydrogens attached to both of those carbons. But since it is a ketone, it doesn't need those. So the other way to write this would be your CH3, C double bond O, CH3. So that would be the condensed structure that I will prefer. Now, technically, these are correct, so if you want to put it in the chain, that is okay. But just like before, when you can completely condense it down into one chain, it makes it more difficult to see. So if you like putting things all into one chain, putting all the branches into one chain, it is not wrong, but I will always prefer to write or show those branches. So you will always see the branches in test questions. But if you write it in your free response questions like this, it is not incorrect. So now we can just talk a little bit more about the common uses. So we talked about formaldehyde being adhesives and bindings for plywood. But the reason why it was used to preserve specimens for the longest time was because it kills viruses, fungus, and bacteria. So that's why it's such a good preservative, is that it disinfects everything so nothing grows in it. So it also then is used to make plastics and adhesives, but we said that fresh polymers may outgas formaldehyde vapor, which is what is toxic. We also talked a little bit about that acetaldehyde. We said it's sweet smelling, but it's actually a little bit toxic to us. So it is present in ripe fruits, especially apples, so that kind of ripe fruit smell that you smell is the acetaldehyde. And we said it was the metabolite of ethanol, so it's what our body breaks it down into when we drink ethanol. It is much less toxic than formaldehyde, but it is still toxic to us. So it's kind of interesting that that kind of sweet fruit smell that we consider from ripe fruit is actually slightly toxic to us. However, you're really not going to interact with enough of it to really make you feel bad when you're eating fruit. Last one we talked about was acetone, and we said it was in our nail polish remover. It is a super solvent, so that's why I said it can dissolve paint, it can dissolve a lot of different organic compounds. So if you have a stain that you can't get rid of, such as like your permanent marker or something like that, Permanent marker is permanent because it's not water soluble. So you can't dissolve it with water. But that doesn't mean you can't dissolve it with other things. It's just not typically dissolved with acetone, or you wouldn't think to dissolve it with acetone. So obviously try a small amount of it on whatever you're going to try to clean first so it doesn't oxidize something and discolor it. But if you just have a stubborn stain on a wall or something like that, try some acetone because it does dissolve a lot of different compounds. It is highly volatile, highly flammable, but it doesn't really pose any health risk. So that's why we could use it on your nails all day long. It will dry out your skin, but that's pretty much all it will do to you. Alright, so that's pretty much it for physical properties of these functional groups. So now we're going to start getting into some of their chemical properties and some of their reactions. So we're going to end this lecture just talking about some preparation of alcohols, and then we'll finish off part 3 with talking about more reactions. Alright, so how do we actually create alcohol? I know, it's cheesy, but I like it. So, dueling banjos. Alright, so let's get into our preparation. So, nucleophilic substitution reactions. So these are reactions when an electron-rich atom, so an atom that has a lot of lone pairs, called a nucleophile. So it's a nucleophile because it's electron-rich. It's very negative, so it likes positive things. So nucleopositive. So you think of the positive nucleus, nucleophile is attracted to positive things. It replaces a leaving group, an easily replaced atom or group of atoms, which are typically chlorine, bromine, and iodine. So your halogens are really good leaving groups. So these groups very easily pop off of carbons and you can replace it with something else. So these are typically called nucleophilic substitutions or SN2 reactions. So let's look at what an SN2 reaction to create these alcohols would look like. Alright, so I have an animation for this SN2 reaction. So we see our alcohol group coming into the carbon group. Here's our leaving group. Those electrons form a bond. These electrons get kicked off, and it forms a leaving group. So notice it's the alcohol lone pairs that come in, drop in to form the covalent bond. When it does, carbon only wants 4 bonds, so it's going to kick off an extra pair of electrons and give it to something that wants it. So these leaving groups are good leaving groups because they like to have negative charges. Bromine likes to have the negative charge because that's how it gets its octet. So this is a very stable compound when it's negative. So the alcohol comes in, drops down. Notice that the hydrogens also moved. So if we look back here, the hydrogens were facing to the left here. But at the end of the reaction, they're facing to the right. This stereochemistry change we're going to look at here in a little bit, we'll see that that actually does change the structure of this compound. So here is that SN2 reaction, kind of just as a flat, non-moving page now. So that a negative charge from our OH comes in, forms that bond to the carbon. I initially have a very, very short time, this transition state, having 5 bonds to that carbon, but it doesn't want it, so it kicks off the electrons, gives them to the leaving group. Like we said, most halogens are good heat-leaving groups. And I form now this new alcohol group with now a negatively charged bromine. I do want you to kind of pay attention to how these arrows are pointing. Notice it always points to where the electrons are going. You'll be working a lot with this in the simulations in the lab. So we said something that is nucleophilic, has extra electrons, and it wants something positive. So notice there's a positive charge here. So it comes into the positive charge and then kicks off those electrons. So if we don't want to draw the whole mechanism, here are the reactions. So if you have a methyl chloride and an alcohol coming in reacting with it, we know the alcohol is going to kick off the chlorine and form a methyl alcohol and a chlorine compound. Or with our bromine, it kicks off that halogen and takes its place. So it's kind of like a single replacement reaction. We are replacing just the halogen group with our alcohol. So wherever you see that halogen, we're going to put an alcohol there instead and have a halogen ion as a byproduct. Alright, so let's give one for you to try. I've got an alcohol and a ethyl bromide. So what is the product of this reaction? So the product of the reaction, then we're kicking off that bromine, attaching the alcohol instead. So technically this is plus a Br minus group, but it is a byproduct, so this is the major product that we are looking for. Now, we actually saw this second way of preparing alcohols when we looked at the hydration of alkenes. So this was our last chapter. So that if we have a double bond and we attach water to it, or we break that double bond with water, one carbon gets a hydrogen, the other carbon gets an OH, and we now have an alcohol. We said we also needed to use Markovnikov's rule when we prepare these alcohols, which, if you recall, means that the hydrogen from the water is going to attach to the carbon with the most hydrogens. So that means that technically we can get two different products for these reactions if I have an asymmetrical double bond that we're using. So asymmetrical meaning that both carbons don't look exactly the same or don't have the same attachments. So in this case, the major product will have the hydrogen attached to this carbon. So that's our major product. Our minor product will have the hydrogen attached here. So some of it does form, but not very much. All right. So like we said, Markovnikov's rule just says that the carbon it's going to get the most hydrogens is going to get the hydrogen from our water to give us our major product. All right, last thing for today, let's give these two a try. So predict the two possible products of these alkenes to form our alcohols. So give me the major and minor alcohol products. Here is the solution for that practice problem. If we look at this alkene, I have a hydrogen here. So we know that the hydrogen from the water is going to attach here, and the alcohol is going to attach here for our major product. And then for our minor product, we'll have the hydrogen attached to this one, and the alcohol group attached to the second one. For our cyclohexene, we got to remember that there's a hydrogen here. So that we don't have any hydrogens on this carbon, the hydrogen would be here. So in our major product, we would attach the hydrogen there as well. And then the alcohol group would go with this methyl group. Then for our minor product, it would replace or add on to where that hydrogen is, and I'd add a hydrogen here. So I know I said that was the last thing we're going to do today, but I forgot about the hydrogenation or hydrogenation to prepare alcohols. So this is the addition of water across the carbon double bond. So just like we had just done with the carbon-carbon double bond, this is a carbon-oxygen bond that we're going to add across. So we can take a aldehyde or ketone and actually add hydrogen across this bond as well. So it's the same mechanism as if this was a carbon-carbon double bond, but instead we're breaking it with a carbon-oxygen. So this hydrogen attaches here, this hydrogen attaches to this carbon. using a platinum, palladium, or nickel catalyst, and we get an alcohol group. We're going to consider this a reduction reaction. I'll kind of give you an easy shortcut of how to identify oxidation and reduction reactions here in another lecture, but we'll see that whenever we add hydrogen, it'll be a reduction reaction. Alright, so that is it for today. Next time in part 3, we're going to look at the reactions of all of these compounds and their new products.